All right, so now what we're going to do is we're going to find the full QR factorization for the matrix from the previous video. So here was the reduced factorization. We found Q, okay? So here's Q, and here's R. And now what we're going to do is we're going to find a full factorization, which means Q is now going to be a 3 by 3 matrix, okay? And R will be a 3 by 2 matrix, so that the product QR will equal A, which is a 3 by 2 matrix. Okay. So to do this, what we have to do is we have to add an arbitrary vector. Okay. And so so the vector that I'm going to add is going to be, so we're going to let A3 equal this vector 1, 0, 0. Okay. And so now we have to continue with this Gram-Schmidt process of making A3 orthogonal to both Q1 and Q2. Remember, these are Q1 and Q2. So we're going to make A3 orthogonal to Q1 and Q2, and then we're going to turn it into a unit vector. Okay, so the Gram-Schmidt process goes like this. We're going to set Y3 equal to A3, and then minus a dot product, where we do Q1 transpose, or Q1 dotted with A3, and then this is times Q1, and then subtract out Q2 transpose A3, or Q2 dotted with A3, and then this is times Q2. Okay. And so these numbers here will be, this will be R13. And this will be R23, although these don't come into play at all as far as our matrix R. So to compute all this, this equals A3 is 1, 0, 0 minus, so this dot product of Q1 with A3, that's easy to compute. I mean, A3 is nice. So really we just get 1 times this root 5 over 5. So that's root 5 over 5. And then times Q1, so that's another root 5 over 5. Remember from the previous video how Q1 was written with root 5 over 5 out in front. And then this is times the vector 1, 2, 0. And then minus Q2 dotted with A3, well, that's already 0. Okay, so really, so A3, which is here, dotted with this vector, that's 0. Okay, so this results in 1, 0, 0 minus, let's see, this squared is 1/5. So it looks like I have a 1/5, or I distribute that into the vector, get this here, and this equals, so 1 minus 1/5 is 4/5, and then 0 minus 2/5 is minus 2/5. And this is a 0. All right, and so now this is orthogonal to both Q1 and Q2, and you can see that by just doing dot products, but it's not a unit vector yet. So we have to make it into a unit vector, so we set, well, this R33, again, R33 will not show up in our R, but we'll label this as R33. This is the norm of Y3. And so this equals a square root of a sum of squares. So if I take these entries and square them, so this will be a 16 over 25 plus a 4 over 25. And then the square root of that is the square root of 20 over 25. And so that equals, in simplest terms, 2 root 5 over 5. Okay. And so now I take Y3 and I construct Q3. So Q3 equals Y3 divided by the norm of Y3. And so Q3 equals first I'm going to write root 5 over 5 times a vector 2 minus 1, 0. And so now I would add this as a third column in Q. And for R, the only thing that changes in R is that we add 2 zeros here. Okay. Remember, I mentioned that R is triangular. So our full factorization, so I'll erase, so you can remember what Q3 is. And so, actually, I'll leave it on the board. Leave it there. And so our full factorization is Q equals root 5 over 5, 2 root 5 over 5, 0, 0, 0, 1, and then 2 root 5 over 5 minus root 5 over 5 and 0. This is Q, and R is same as the previous R, except now we include a row of zeros, and I'll ask you to check that A equals Q times R.